Hi everybody, this is Dr. Nigro here with the Screencast for Chem calculations. This one's going to deal with calculations and colligative properties. All right, so before we get started on those calculations, we should define a colligative property. All right, remember a colligative property is any physical, and that's important, physical property of your solvent. I'm going to capitalize that to help us keep that in mind. All right, that changes when a solute is added. All right, so the physical properties of the solvents are well known. All right, boiling points, freezing points, melting points, conductivity, all these different physical properties. Some of those physical properties are influenced by the presence of a solute. All right, so again, some examples that we're going to deal with: vapor pressure. All right, and if vapor pressure is influenced, then so is your boiling point. All right, we will represent as TB. All right, and chances are if one of your state change temperatures is influenced by the presence of a solute, then so is the other one. All right, so freezing point. All right, and we represent freezing point with TF. All right, now these properties change based on the type of solute that you add. So we have solutes that can ionize or dissociate in solution. These are our ionic compounds and our acids. And when that happens, we don't get just one particle of solute, we get multiples because they split. All right, and those have a greater influence on this change in our physical properties than a substance such as a covalent compound that only splits, that doesn't split at all, basically dissolves and gives you single particles, such as sugar. All right, now to calculate the change in temperature, so we'll look at boiling point first. All right, we need to consider three things. We need to consider whether we have something that splits into ions or not. All right, and we cover that by using something called the Van Hoff factor. All right, and this is usually a whole number, and that whole number is a count of the particles that form when that particular solute dissolves. So for example, something that is non-ionic, such as glucose, C6H12O6, when that dissolves in water, the individual particles of C6H12O6 are pulled off, surrounded by water, and you get one particle for every one piece of our solid. All right. If we have something that's ionic, like sodium chloride, every time that one particle of NaCl dissolves, it splits into two ions, the sodium ion and the chloride ion. So for every one NaCl, we get two ions. All right. So for the I value, the Van Hoff factor for NaCl, it would be 2. All right. If we had instead aluminum chloride, which is AlCl3, for every one AlCl3, we get 4 particles, 1 aluminum and 3 chloride. So that would have a Van Hoff factor of 4. All right. In addition to recognizing whether something will dissolve into a single particle or multiples, we need to know the molality of that substance. So remember, that's moles of solute divided by kilograms of solvent. And then we need to know a constant that is dependent on the particular solvent. Kb is a constant that depends on the ID of the solvent. All right. These are going to be given to you. They also can be looked up using Google or in your textbook. All right. So once we know the Van Hoff factor, the molality, and Kb, we can use those values to calculate the change in the boiling point. And remember, that change is equal to the final temperature minus the initial. So this is the no solute, and the final is the plus solute. All right. Now, speaking of this, one of our main solvents that we use is water. All right. So it's very handy to know the freezing and boiling points of water. All right. So don't forget that for water, the boiling point is 100 degrees Celsius and the freezing point is 0 degrees Celsius. All right. So just keep that in mind. Kb will give you. All right. Now let's look at the formula for Kf, the change in freezing point. All right. It's going to look very familiar. All right, the change in the freezing temperature is equal to the Van Hoff factor again, times the molality of the solution, times a constant, but this time the constant is for freezing. All right, so we need to know what that value is, just like we need KB, and it should be given in the problem. All right, now once you're working these problems, you need to watch out for ionic compounds or acids. Both of those split into multiple ions. The ionic compounds dissociate in solution, the acids ionize. So we need to keep track of the number of ions that are present. All right, so let's try one of these. What is the boiling point of a 5 molal solution of glucose in water? The Kb for water is 0.512 degrees Celsius per molal. All right, so let's see what we know. We have a molality of 5 molar. All right, we have a Kb value for water of 0.512, and that's degrees Celsius per molal. All right, we need I, so we look at our substance. We've got C6H12O6, so this is a covalent substance. It's not going to split into additional particles. There's no ions that will form. So our Van Hoff factor here will be 1, and our unknown is the change in that temperature. All right, so we're going to use our formula, delta TB equals I times molality times Kb. We're going to plug in what we know. So we have 1 times 5 molal times 0.512 degrees Celsius over molality. All right, so our change in boiling point is going to be equal to 2.56 degrees Celsius. All right, now in class, we've talked about elevation of boiling point, because remember, when you add in a solute, that solute can block access to the surface of your liquid for those solvent particles. So that means you get a lower vapor pressure. And if you have a lower vapor pressure, it's going to take more energy to reach atmospheric pressure. So the temperature required for boiling is going to go up. All right, so we get a boiling point elevation. All right, so that means when we want to determine what the actual boiling point is of this solution, all right, we know that the change was 2.56 degrees. All right, we don't know what our final temperature is, but I know that the initial or the original boiling point for water was 100 degrees Celsius. So if I add 100 to both sides, then the final boiling point for this solution is 102.56 degrees Celsius. All right, so make sure you do that last step too. Don't just tell them to change. It asks for what the actual boiling point was. All right, so let's slide down to our next problem. All right, this one's a little bit different. How many grams of C2H6O2 must be added to 4,000 grams of water to reduce the melting point to negative 40 degrees Celsius? The Kf for water is 1.86 degrees Celsius. All right, so let's start by looking at the change in that freezing point. All right, we have now gone down to negative 40 degrees Celsius. All right, our original freezing point for pure water is 0. So the temperature change here was negative 40 degrees Celsius. All right, we are given nothing for the molality. All right, so that's an unknown. All right, the Van Hoff factor, we again have C2H6O2, a covalent compound. It also tells us it's a non-electrolyte, which means it does not ionize. So we're going to have a Van Hoff factor of 1 here, and we're given a Kf for water of 1.86 degrees Celsius per molal. Now, technically, this should be negative. All right, so I'm going to use negative 1.86. All right, if I'm trying to find the grams needed to be added to this 4,000 grams of water, I need the molality, because if I can calculate the molality, then I can use that to find the moles of my solute, and then from there go to grams. All right, so I'm going to start by using my temperature change formula, except this time for freezing. So I times M times Kf. Nope, and then I wrote Kb. Sorry about that. Kf. All right, so negative 40 degrees Celsius equals 1 times my unknown molality times negative 1.86 degrees Celsius per molal. All right, if I divide that 1.86 over, I'm going to find that the molality of this particular solution was 21.5 molal. All right, now that molality is equal to moles of solute divided by kilograms of solvent. So 21.5 molal is going to be equal to my unknown amount of solute divided by my kilograms of water. Now I know that I have 4,000 grams, so that's the same thing as 4 kilograms. So the moles of solute that must be present in this solution are 86.0 moles. That is a lot. All right, last step, I want to know grams. So I'm going to take the moles of my solute and I'm going to convert those to grams. Using my periodic table, I know that 1 mole of C2H6O2 has a molar mass of 62.08 grams. All right, so I'm going to multiply 86 times 62. Wow, 5,340 grams of C2H6O2 will be needed to add to my water if I want to get water's freezing point to drop from 0 degrees to negative 40. All right, now I don't know if people know about antifreeze. Most of you can drive now. All right, but antifreeze is what we use to keep all the water in the lines of your car from freezing. All right, so we put antifreeze in our cars to help combat freezing due to cold temperatures. All right, so now let's look down at this last problem, problem number 3. All right, this one says, what is the boiling point of a solution produced by dissolving 45 grams of CaCl2 in 500 grams of water? The Kb for water is 0.512 degrees Celsius per molal. All right, so let's see what we know. All right, U, B, and I realize I haven't done that for the last two. That was I should have done that. So our solute is calcium chloride, and our solvent is water, and the sum of the two gives us our solution. All right, we have 45 grams of our solute dissolved in 500 grams of our solvent. All right, if we want to calculate the boiling point, we're going to need to figure out the change in that boiling point. All right, so that's our goal in this problem. To do that, I need a couple pieces of information. I need the molality, which I don't have. All right, I'm going to need the Van Hoff factor, so I better go check that. So calcium chloride, all right, this is an ionic compound, which means it's going to split into ions when it dissolves. In this case, I'm going to get 1 calcium cation and 2 chloride anions, so I'm going to get a total of 3 ions, all right, which means it has a Van Hoff factor of 3, all right? And then finally, Kb, which is given in the problem for water, 0.512 degrees Celsius per molal. So I'm going to start by figuring out the molality. Once I know the molality, then I'll be able to calculate the change in boiling point, and then I can figure out what the new boiling point is. All right, so molality, moles of solute divided by kilograms of solvent. All right, and if I look, I have 45 grams of calcium chloride, but I do not have the moles. So I'm going to go off to the side and take my 45 grams of CaCl2, use my periodic table, and find that 1 mole of CaCl2 has a molar mass of 109.9 grams of CaCl2. All right, so I actually have 0.82, oh no, wait, 0.41, sorry, off by a little bit, 0.41 moles of this substance. All right, so I come back to my formula for molality, put in 0.41 moles of solute. I have 500 grams of water, but I need kilograms, so I divide that by 1,000, and I have 0.5 kilograms of H2O. All right, if I divide the two, I find that the molality of my solution is 0.82 molal. All right, so there's part one. I've got the molality. Now I'm going to use it to calculate the change in my boiling point. All right, so remember that's going to be equal to the Van Hoff factor times the molality times Kb. All right, so the Van Hoff factor here is 3. We found the molality to be 0.82 molal, and for water, the Kb is 0.1512 degrees Celsius molal. All right, so our change in boiling point is going to be 1.26 degrees Celsius. All right, so again, remember, that change, 1.26 degrees Celsius, is equal to our new boiling point minus the original boiling point, which for water is 100 degrees Celsius. So our final boiling point should be 101.26 degrees Celsius. All right, so you can see that problem had quite a few steps. You had to use the mass of your solute to find the moles, and then the moles of that in kilograms of the solvent to calculate your molality. Then you use that molality to find the change in temperature of your boiling point, and then added that to your original one to elevate it to 101.26. Okay? All right, remember, colligative properties such as boiling point, vapor pressure, freezing point are influenced by the presence of a solute within the solvent. If that solute can be ionized, such as a acid, or it can be dissociated, such as an ionic compound, then you have to include the number of particles as the Van Hoff factor. If you instead have a covalent compound, which only produces a single particle when it dissolves, then the Van Hoff factor is 1. All right, do not forget Kb has to be given, as does Kf, and the boiling point for water, pure, is 100 degrees Celsius, and its freezing point is 0.